we'll be looking at AC power and how we calculate that based on a sinusoidal voltage and a current waveform. Here is a cosine wave, and we're going to say this is our voltage waveform. Okay, so if we want to look at power, we need to look at the voltage and the current waveform. So the current waveform will be similar, but in many cases it will have an offset. So here we're going to center this right at 0, so that's where there's no phase shift here. But we could potentially have a phase shift. So let's say, I'm really bad at drawing these, I apologize. But okay, so something like that. And the magnitude may or may not be the same, I'm just drawing it similarly. But the important thing is that there is a phase shift here. So this difference here between this, we'll call this phi. And I want to define here, phi is the phase shift between the voltage and the current, and it's defined by the phase shift of voltage minus the phase shift of the current. So in this case, our phase shift for the voltage is 0, and then we have, in this case actually, this phase shift I would be a little bit negative. So it's because it's a little bit ahead here. So if you do the math for all this, you'll see that this value would have to be negative. So we're going to draw the current waveform. We're using these root 2's because these are the RMS values. And again, here we're going to use cosine, but now we have a phase shift. And so if you do all the math again, you'll see that you actually want to subtract the phase shift here. And if you put this into here, you would get this minus phi v and a plus phi I. And if here we have our no phase shift on the voltage, we'd actually just get plus a phi I here again. So if you trust me though that these are our waveforms for this, now we're going to go ahead and calculate the instantaneous power. Okay, so to do that, we're going to do instantaneous power, so P of t, and all we have to do is multiply voltage and the current waveform together. Okay, easy. So let's plug in these values. So we're multiplying these together. We're going to give a root 2, and we're going to square it, so it's going to be just 2. Then we have v and I, the RMS values. And then we have 2 cosines, so let's just multiply them together. Oops. So now we have the cosine of omega t minus our phase shift between our 2 waveforms. Okay, so this is a little bit, I don't really know what to do with this. Hey Valerie, do you know what to do with this? Valerie says to use the trig identities, which she has already written on the board for us, so thank you very much. So we have a trigonometry identity here, trig identity, and we see that if we have the cosine of a and b multiplied by each other, we can simplify it into this form. So we can take that and plug it in here. So we'll do that. So first we'll just make this 2 vi, and now we're going to break apart this. So we're going to get 1/2 here, and we're going to do the cosine. We need to subtract these 2 values, so we get omega t minus omega t, and I'm going to carry the negative, plus phi. Okay, and then we're going to add cosine, and they're going to add these 2 values together. So we're going to get, I'm going to do some pre-adding, so we're going to add these together, 2 omega t minus phi. Okay, we'll notice that these will cancel out with each other. So we will be left with this. Cosine of phi plus cosine of 2 omega t minus phi. And I, of course, forgot to cancel these out, but we see that we are going to be left with just the RMS values here. Okay, so the instantaneous power is equal to, and we're gonna distribute this out, so VI cosine of the phase difference, V, plus VI cosine of 2 omega t, so 2 times our frequency before, with some phase shift. Okay, so this is our expression for our instantaneous power. This is our DC component. So this is some offset, some DC offset, so we can think about it like this. There's some DC offset that's based on the RMS voltage and current, and then the phase difference, the cosine of the phase difference. And then we have some oscillating waveform that is 2 times the frequency here. So this is the oscillatory component. So we have some sort of oscillation. Okay, so if now we want to look at the real power, the average power, we can actually look directly at this equation. So now we want to find the real power, so that's P, the average power. Well, we have this DC component, and then we have this oscillatory component that's based on a cosine. If we take the average of a cosine, it's going to be 0. So actually, we can completely ignore this, and then we're just left with the DC component. So the power, the average power, is actually VI, and then the cosine of our phase difference. So I hope that kind of made sense. We're looking at the 2 waveforms of voltage and current. Just looking at the power waveform, we see that we get a DC component and an oscillatory component. When we want to just find the average power, we can get rid of this oscillatory component and just look at the DC component. So these are the 2 equations for power, the instantaneous and the average power of an AC waveform.